and hand it over to Jonathan.
Hi, my name is Jonathan Blythe. I'm the co-lead for the tech team in IARPC Collaborations. And we've been in operation here as a collaboration team at IARPC for 2 or 3 years now. It's a fairly new team as part of the new 5-year research plan. We're now midway through. And one of the things we tackled from the beginning, since this was a new team, was to help us define what technology means in the Arctic research context. It means several things to different people, and one way to do this, to define this, is to ask leaders from the community from different sectors. So we've surveyed leaders from private sector, academic, also government sector, and today we've asked Philip McGillivary to give us a talk. He's a leader in Arctic research. Give us a talk on his perspective. I'll give a short biography before we start. So he was in grad school at the Institute of Ecology at the University of Georgia. He had postdocs sponsored by the Office of Naval Research at UC Santa Barbara and NOAA at the Monterey Center for Ocean Analysis and Prediction. His career started, he took a position with the Office of the Secretary of Defense, and in 1996 was appointed as the icebreaker and Pacific Area Science Liaison for the Coast Guard icebreakers. He's also double-hatted as chief scientist to the Office of Naval Research International Collaborative Engagement Program for Polar Research, or ICEPAPER. So he has a lot of really cool anecdotes and things to show us. In particular, I asked him to kind of take a step back, as many of us have seen his talks at AGU or the Polar Technology Conference, where he really has a lot of knowledge and expertise in different technologies and can kind of wow the audience. But I asked him to take a step back and look at the policy perspective and research priorities, especially under the new administration. So I hope we'll be able to have some time also reserved at the end for a nice dialogue in this IARPC collaborations context. A very unique space for us to share ideas and find common interest and opportunities that we might not all otherwise get. So without further ado, I'll pass it over to Phil. Thank you, Phil.
Okay, good morning. I am the science liaison for the Coast Guard and for the Coast Guard's icebreakers. And so I've been thinking fairly deeply about how we can improve our observations in the polar regions and what technologies we have available for those. So let me go to the first slide then, the next slide. So looking at what we're trying to do and what are the challenges for us. First, the challenges for us right now are immediately responding to administration presidential executive directives. And so on April 9th, there was a Maritime Action Plan. In Section 18 of that plan, DoD, the Homeland Security Department, the Coast Guard were given 90 days to draft an Arctic security plan. So that is underway now, and some of the things I'll be talking about relate to that goal. There was also an executive directive on modernizing acquisition on the same day and spurring innovation in the defense industrial base. And that called for broader use of other transactional authority. And for those of you who don't know what that is, that means that you don't have to get 3 bids for something, and you can let a contract up to a certain amount of money, which is pretty significant, within 45 days. And for the Coast Guard, and others in the government, the Defense Innovation Unit is in particular really good and very well experienced in doing OTA purchases. And also specific to the Coast Guard, we have something called the Force Design 2028. And what that is a reorganization of the Coast Guard It's also focused on acquisition and contracting, and it calls for greater cooperation with the Defense Innovation Unit, specifically to allow us to accelerate purchase of new capabilities to leverage disruptive technology. And in my case, and this is particularly unmanned systems, to include high altitude, long endurance aircraft and aerostats as well. And the other thing I should mention about the Force Design 2028 is it formally sets up a new branch of the Coast Guard, a new division within the Coast Guard for robotics and autonomy, which had been discussed, but we didn't really have personnel and it wasn't a formal thing. And under this rearrangement, it is now. So next slide. All right, so from my perspective, as I mentioned in that first goal, we do have a national security issue. And so we in the Coast Guard are attempting with the other maritime agencies to maintain persistent maritime domain awareness. And this is one thing for the Arctic EEZ, which is certainly huge, but when you look at the extended continental shelf area, that gets to be a very large area. And that includes maintaining awareness of both ships and aircraft, as well as submarines. But the more critical thing right now that we're trying to deal with is persistent maritime domain awareness for critical undersea infrastructure, specifically things like undersea communication and power cables that might be bringing offshore wind or tidal power ashore. So in addition to that sort of broad area maritime domain awareness, we also are, as part of the Coast Guard, supposed to maintain shipping and commercial transport capabilities. And there's been and is an ongoing large effort now to coordinate satellite sea ice data and speed up the analysis of that using machine language learning and artificial intelligence. And the goal is to enable real-time ship routing, excuse me. So right now, you get the satellite images come in, they tend to sit around for a couple of hours before the people on ships actually get them while they're being analyzed. And then by the time you get them and you're able to do something, you may be in a completely different situation. So the goal is there are more satellites going up for sea ice, and they're going to have more coverage. So with that greater coverage, we'll have a lower latency time, especially if we can speed the analysis. So that is an effort that's ongoing with several federal agencies right now. And this also gets back to the other Coast Guard requirements for responding to oil spills, maritime search and rescue operations, and natural disasters in the Arctic as well. And we have seen our share of search and rescue and natural disaster effects go up in Alaska. And the greatest risk the Coast Guard, the greatest threat the Coast Guard feels right now is from oil spills from all of the Russian ship traffic, which I'll talk about a little bit more. And then the ongoing issue as a challenge is just communication. How do you get communication out of the Arctic, and how do you get communication from things that are underwater and maybe under ice, and how do you get those communications done in near real time as possible? And so while these are all national security issues and challenges, I would point out, as I do on the last couple of lines in this slide, that the technology requirements to address the national security challenges are not really significantly different from those for scientific monitoring in the Arctic ecosystems. So going on to the next slide, I'm going to review 4 case studies from my perspective for these security challenges. And the first one I mentioned is undersea communication cables and their protection. So we have the quintillion fiber optic cable that goes around Alaska to Utqiagvik, but there's also a new polar connection cable that will run from Finland to Japan via a trans-Arctic path, basically across the North Pole. And the purpose of this cable is to provide a backup. Like 85% of the cables that are communication cables that are going from Europe to Asia go through a section of the Red Sea that's only 2 kilometers wide and very susceptible to all kinds of damage. Now, one of the challenges we have is that the Russian and Chinese vessels have been accused of cutting communication cables oil and gas pipelines in Europe and including in the Arctic several times. And it says several times also specifically in the Arctic in the past couple of years. And one of the other problems for those who have been paying attention to this, and it took a while to get people to start doing that, but a little bit late actually, turns out that the Russians and Chinese have both been doing surveillance of all of our fiber optic cables in the Arctic. And that's in part probably because those cables are connected to US missile radars. So one of the challenges here is how can we protect these fiber optic communication cables when those, like for the Polar Connect, are going to go from Finland all the way to Japan over thousands and thousands of kilometers. So I'll show in the next slide here is the cable route for the Far North Fiber and the Polar Connect. And you can see the green is the Polar Connect cable, and you can see it has that trans-Arctic route. So that's a long lot of cable in a very inaccessible area to be protecting. So I'm going to move on to the next slide, which is another one of the 4 case studies that I have here. And this deals with mineral resources on the extended continental shelf. And so we used our icebreaker, the Healy, and also worked with the Louis Saint Laurent to map the extended continental shelf in the Beaufort Sea and the Chukchi Sea. And this is to be submitted under the UN Law of the Sea to make the extended continental shelf claim. However, the US has never ratified the Law of the Sea. And so some countries, specifically China, have said outright that they don't acknowledge the legitimacy of the United States' extended continental shelf claim. And the reason that this is important there is in that second bullet. While they were doing the mapping, they did some rock sampling and found very thick layers of manganese crust. And the manganese crusts are on the Chukchi borderland all the way north at the very edge of it before it drops off into the Beaufort Sea. And they have a chemical composition that's very different than the manganese crusts generally in the Pacific. And they're still full of some of the rare earth elements that are required for a lot of technologies, which we have been importing from China, which is now reducing that availability. And I provided the reference there. Meanwhile, one of the other challenges is that China they have a very capable long-range AUV, and they've been deploying that in the Arctic in places like the Gackel Ridge to map both the bathymetry and the rare earth elements. And so they've been up there mapping, and we know that they mapped along the Gackel Ridge, and we think that they have been mapping elsewhere, and our surveillance hasn't been good enough to really have that information completely available. But the question here is, how do we both map the manganese crusts, including their thickness, not just their spatial distribution, so we can quantify the amount of minerals that is present, and how can we secure those in this area of the northern Chukchi borderland, which is quite a ways up into the Arctic. So that's the second case study. So moving on to the third case study that I have on the next slide. So this is the issue that gets back to shipping and the whole effort about changing Arctic sea ice. So the Russian oil shipping through the Bering Straits increased 15-fold from 23 to 24, 2023 to 2024. And it's expected to continue to increase. So Russia is opening up a couple of new liquid natural gas plants. And so some of the ships that they're using are uninsured, some of them are very old, and there is a huge risk of oil spills. As I mentioned, Coast Guard in Alaska, this is their #1 worry right now, is that there's going to be a spill in the Bering Straits. And so we were fortunate that Department of Homeland Security over the last couple of years realized that we really weren't up to snuff with the NOAA IRMA oil spill model. It couldn't take in data from unmanned aircraft on where the oil spills really were, and it had never included sea ice. So over the last several years, funding from Homeland Security brought it up to where it can ingest unmanned aircraft data in real time, and it can also include sea ice dynamics in a realistic way. So we can better predict where the oil is going, because we know if there's a spill in the Bering Straits, it's going to be on the coast of Alaska within literally hours. And so one of the challenges is, as the Arctic sea ice is moving around and we are getting increased satellite imagery and machine language learning and AI, how can we monitor the sea ice to improve ship routing and reduce the risk of oil spills? And that's the third case study. The fourth case study is in the next slide and is related to that. So we'll go to the next slide. And so this has to do with just understanding Arctic sea ice and what's going on up there and how it's affecting the ecosystem. So we know, for example, that air-sea gas flux, marine mammals, particularly, of course, ice seals, and primary productivity are all strongly influenced not just by sea ice, but by sea ice ridging. In icebreaker operations, we say that it's not sea ice that stops our ships, it's actually ice ridges. So that's been a focus of mine for a long time. And I am delighted to report that although the data has not been really very available, in February, there was a great study by Thomas Crimpen of the Alfred Wegener Institute. He looked at 3 decades of helicopter and aircraft imagery to look at ice ridging. And he concluded that there was a general decrease in ice ridging, but the results were actually more complicated. He actually found that there was more ridging in thinner sea ice now, and it ridged 4 times more than older sea ice. But the older sea ice has been melting away, and that's why there is a slight overall decline in sea ice ridging. But as I noted, there's been much more ridging in the thinner sea ice. And so it also affects how the sea ice melts, and it surprisingly causes it to melt back faster. So that's a great article. So one of the challenges that I have on my desk is in order to not only help with ship routing, but also to understand air-sea gas fluxes, how marine mammals and primary productivity and mixing of nutrients are affected in the ocean. How can we really understand sea ice better? And how can we especially understand ice ridging? So those are the 4 case studies that are on my desk that I thought we should maybe take a look at. And then we can have some discussion, and I can suggest maybe some methods that I'm looking at to try and get at some of those challenges. But I'll turn it back over to you, Jonathan.
Great, thank you. Yeah, you can see we kind of coordinated this. Phil has a wealth of knowledge, and I really appreciate him kind of highlighting 4 research questions. And the intention is to engage with the audience here on any of these questions, or maybe you can suggest a 5th one. I don't know. Does anybody have any questions or follow-up to any of the topics he's raised?
I didn't bring up fish issues and fisheries, but that's definitely a consideration politically right now.
For sure. And I will remark that a lot of the topics you've raised have a overlap with BOEM interests in the Arctic, and all of them do. In fact, the first one having to do with infrastructure, well, it's more relevant to where we have offshore development, but they're like in the Atlantic with wind farms, with oil and gas and Gulf of Mexico, there's always the pipelines or communication or electrified cables that we are worried about, and so that's also applicable to us. But the fisheries issue, there's a question from Elizabeth in the chat. The Arctic fisheries, BOEM has done some work, of course, with looking at characterizing Arctic fisheries. And Phil, what work are you looking at with the Coast Guard to characterize that?
Well, it's actually, the Coast Guard has an interest in, we have a legal mandate to prevent illegal fishing. And so one of the questions that is one of the issues coming up about the Central Arctic is you're allowed to do experimental fishing, but exactly what that is and how many vessels you're able to use with that, that's not spelled out. And so there is a pretty significant concern that fish species are migrating into the Arctic. We know that they're moving around, and the Chinese have indicated that they are ready to begin experimental fishing in the Arctic. But how do we have a way of monitoring that when we don't have anybody on those ships? And one of the other issues came up yesterday at the Marine Technology Society's eDNA, and they have been traditionally going out with NOAA and dragging nets around to assess fish populations. But one of the new methods that is being considered is deployment of autonomous underwater vehicles and or moorings with eDNA capabilities on them. So that's one of the things that I'll be talking a little bit more about the AUV methods, but we are already seeing, and I know myself that some of the programs I'm involved with are going to be putting eDNA buoys out into the Arctic along with passive acoustic monitoring systems to see where the fish are going and where the marine mammals that eat them are going and when they show up and how they change. And this has to do with the whole structure of where the polynyas are in the Arctic and how those may be changing in the future, and how increased ship traffic in the Arctic may result in the animals responding and moving away from the increased ship traffic. And we're definitely seeing increased ship traffic. I didn't give the numbers for the increased ship traffic in the Northwest Passage and even the Trans-Arctic route, but those are very significantly increasing. So that's a little bit of might be getting at fisheries.
Yeah, that's really interesting. I mean, I see a lot of common threads with foam research in the Arctic. So I see Carrie, she had her hand raised. Do you want to ask? Oh, sorry, he had his hand raised. Please ask your question.
So, yeah, thanks for the presentation. So, just curious, like these 4 or 5 case examples you've given, how do they fit it? Are they like kind of representative of the focus of the Coast Guard, or are they representative of kind of areas that you're interested in, or how does it fit into the kind of bigger context of the Coast Plan for Bering Straits and the Arctic and North?
I do work for the Coast Guard, and so, like I said, we're under the Coast Guard and Homeland Security are under a presidential mandate to come up with a plan for how to secure the Arctic, and that security involves both the cables, it involves shipping, and it involves oil spills. So those are the areas. But as I'll be talking about in a little while, the issue of how to deal with those questions involves technology development that can be used for scientific monitoring as well. One of the other issues that the Coast Guard is responsible for is trying to reduce whale ship collisions. And I've written a number of papers on that, and we have some technologies that I've been focused on using unmanned aircraft to do that. And we're going to be, I'm trying to get some high altitude aerostats and unmanned aircraft up in the Arctic that could provide more persistent surveillance of where the whales are going. So we have a real-time awareness of that, and we can try and warn ships not that there might be a whale in their path, but that there actually is one. So there's some changes that, you know, it gets back to shipping for the Coast Guard because that's part of our effort. But those capabilities from aerostats can be used to image. They have very high resolution sensors. They can be used to count seabirds. They can be used to count marine mammals and other things as well. So same kind of concept. I hope that sort of answered the question a little bit.
Since you came off video, Carrie, can I ask you a question on what your interests are, where you see possible intersections with Coast Guard's work?
The first example kind of caught my eye. I mean, all of them kind of did, but I just was curious when you started talking about marine domain awareness and then focusing specifically on the, you know, the existing underground infrastructure. The reason why, because the marine domain awareness world is much bigger than just, you know, just that specific example. A couple of things that's one direction that I was thinking about, but the other thing is that the actual undersea cable was 100% funded by private interests and a lot of international interests. So that's why I'm wondering why is it the Coast Guard's responsibility to ensure that it doesn't get broken? Because I remember when they were laying that cable, they had a company from Italy or in Louisiana who were laying the cable, and they had never even heard of ice gouging before. That's why the whole project was held up for a whole year, and Kotzebue was, hey, what are these big cannons that we're finding? Oh, that's ice gouging. So like that there was no the federal permitting or everything didn't oversee that whole laying of the cable. So I just see that a lot of the problems we're having is because of that, and I just wondering why is it a federal responsibility now to maintain the safety of that cable?
So I can address that for you. So technically, those communication cables are considered critical infrastructure, just as they would be if they were for offshore power. And so the responsibility for those lies within the Department of Homeland Security in a group called the CISA, which is Critical Infrastructure Security Administration or agency, I forget which. And so it's in Homeland Security in CISA. And if you go to Homeland Security and CISA and you look at what maritime assets do they have, the only maritime assets that they have, especially in the Arctic, is the Coast Guard. And the Coast Guard hasn't embraced this, but they know it's on the table, and we have had some workshops to discuss this. As regards whether or not what the role of the companies should be, that's an ongoing subject for discussion. There is intended to be a partnership with the companies, and I have been working with a smart cable group that is funded by the Keck Foundation to try and see if we can increase the technological capabilities to make the cables themselves smarter about where they're at risk and what's going on. What was I going to say? Oh, the other thing that I touched on, but we can't talk about too much, is these cables do connect to our missile radars. So that's a very clear national security issue. They may be privately owned, but if they're bringing our radar data for where missiles are coming across the Arctic potentially at the United States, there is a very real national interest for Homeland Security, and that's where CISA comes in. So I hope that clarified that a little bit. It is something that's still being worked out, and one of the technology issues, and this is the stuff we'll be discussing in a little bit, is how do we do this? Or how might we do this?
Yeah, this is one of the perennial themes in IARPC is local engagement on federal activities. So a very appropriate question for this group. We have a couple more questions, and then we really have to move on with the presentation. So I have these folks in order. Skylar was next.
Yeah, so my question is, across all of these, you kind of touched on like different ways in which you're going to include like some sort of unmanned vehicle technology. And so my question is really about whether the capabilities we have in that domain are sufficient, or whether there's like ways we need to be advancing our capabilities in terms of these vehicles and how we use them in order to suit the Arctic environment.
Okay, so I class unmanned systems into three categories. Unmanned surface vessels, those have been used, and they've been used for fisheries in the Arctic quite a good bit. The wave glider is an example of one of them. And there's another one that's also been up there taking fisheries data. Those are great as long as there's no sea ice. Then the other classification that has been the focus of most work has been unmanned aircraft. And we are working in areas of unmanned aircraft operations right now. I've been working very hard with the military to get what I refer to as a Predator, which is the very large MC9 aircraft up into the Arctic. So far, they have never been in the Arctic, so that is a challenge. We do have some plans to get them up there. And then NASA has had some unmanned aircraft that are high altitude, medium endurance. And we're trying to get some high altitude, long endurance aircraft up there. And like I said, also some aerostats. Those discussions are ongoing and will probably happen in the next couple of years. One of the things we'd like to do is to get a high altitude, long endurance aircraft or an aerostat or a pseudo satellite up there that can look at the big picture from high altitude and have a connection with a lower altitude unmanned aircraft, maybe a medium endurance or even a small one that can take more specific data and, for example, be at an oil spill site or track a search and rescue case or something like that. So I think that's coming along. The other part of the talk I'm going to talk about today is the real challenge that I see, which is the development of autonomous underwater vehicles. And we have some of those that are long range. They have been operated in the Arctic a little bit. Canada has operated theirs a little bit, a couple of times, but we're talking a couple of times, not really incorporated into a national capability yet. So that is one of the things that I'm going to talk about a little bit more.
Okay. Last question from Mark. I have to admit, I asked Mark to come and ask this question. So please go ahead, Mark.
I could wait till the end if that's a better time to address. Mine's really more of a comment than a question.
Go ahead. Let's figure it
Okay,
out now.
great. I'll be brief. So my name is Mark Leon. I work at the Bureau of Ocean Energy Management. I'm an exploration geologist with the Marine Minerals Division. My background's in resource assessment and evaluation. So speaking to case study number 2, the challenge, how do we map and secure the U.S. Arctic ECS mineral resource? So through OXLA and its recent expansion through definitions, BOEM has responsibility of the ECS as well. And so the way that we map resources for assessment and evaluation purposes is largely done in partnership, both with internally with our colleagues in the Office of Environmental Science, but also we have a long history of partnerships with BSEE, USGS, NOAA, and many others. So I think might be a very good opportunity to leverage expertise and resources and identify overlapping interests. I'm particularly interested in your unmanned vehicle program that you said was recently maybe expanded or bolstered. And just real quickly, I'd like to mention that I host an interagency workshop for critical minerals in the Washington, D.C. area every year where we have program managers from around government. We discuss how programmatically we might be able to collaborate and identify overlapping interests and goals in places where we can leverage resources. So I saw some of my colleagues. Oh, is Guillermo on there? Hey, Guillermo, welcome. And so I was just about to open up the floor to anybody from BOEM or BSEE or anybody else who wants to maybe speak to the collaboration and our successes and maybe identify places where we might be able to do work in this area as well.
I know Guillermo.
Yeah, this
Hi, Phil.
hey Guillermo. Do you have anything to pile on after Mark's introduction there, or?
No, not right now. Thank you. I apologize for joining late, but we can talk offline.
Yeah, I think this topic for critical minerals is we're all trying to feel around, find our footing on this as a new agency priority. So maybe something for another time, but it's good to highlight it now. So if there's no more, we really actually have to get on to the rest of the presentation because we have, we're coming up on the end of the time. So
Okay.
Bill, go ahead.
All right, I'll try and get through this as quickly as possible. We don't have to read everything on these slides. So one of the things that I mentioned is that we're really focused on using long-range autonomous underwater vehicles. So one of the problems is there's no underwater GPS, and especially if you're under ice, it's hard to get that information to your AUV. So we've been looking at a couple of ways of doing that. The first of these is ELORAN. ELORAN is like GPS, but it's 5 million times stronger, so it can't be jammed. And it also can operate from the Loran-C antennas the Coast Guard still has out there because Congress never let us take them down. And so the transmitters fit in a 20-foot container, and the signal goes out 100% to 1,200 kilometers, starts to fall off some by 1,600 kilometers. There is a commercial vendor for them, and we did some tests in February and May of last year. It does go underground. It also goes underwater. We only had a test condition for it, a container for the sensor at 30-foot pressurized, but it had very strong signal to noise ratio. And we believe that you can get a GPS position from ELORAN to at least about 100 meters. And so one of the ways of doing this is to, one of the goals we have is to put an AUV underwater and look at ice ridging and roughness. And roughness is another thing that's biologically important as well. And try and have an unmanned aircraft look down. And if we can get the position of them from above the ice and below the ice at the same place in the same time, that's something that we're looking at doing. ELORAN is going to be sold as a service. So the company will put these in out, and then you'll just pay a small amount to get the information for your positioning. The UK has contracted for half a dozen of them around their entire coast. There are a couple of them contracted for the mainland of Norway. I'm trying to get a couple more from Norway to improve the accuracy by triangulation. So we'll go to the next slide, which just shows very simply a picture of, there are, I think, 19 ELORAN sites on the continental US. And then there's a picture that shows all of the ones in the North Atlantic there. And there's a couple missing there. All right, and then we'll go to the next slide. So as another way of getting this is muometrics. This is a method developed in Japan. Muons are cosmic rays. Basically, they penetrate pretty much anything. This particular method requires the cosmic rays to strike at an angle of less than 30 degrees from the vertical. That condition is well met for latitudes above 45 north or below 45 south. And so it's great for polar stuff, and it should work really well into the auroral oval because you get even more muons then. The sensors are very simple. They're glass plates. The muons pass through a liquid between the plates. They give off Cherenkov radiation, and you can track the path of the lights, and that will give you your position on the planet. Right now, they're about the size of a cookie sheet, and they cost about $5,000 a piece because they're all custom made. So the great thing is that they're completely unaffected by temperature or pressure. So if you have these sensors, you don't have to worry about that. You can use them at any depth. We believe that they should work to a depth of about 1,000 meters and give you a position with an accuracy of about a meter. So it's really a great system for deeper water work. So the key thing is that ONR has been funding this. They've only done one test. We need to do some more tests in the Arctic, see if we can reduce the size of these and use smaller detectors. The good news about the detectors is that they use almost no power. So that makes them, they could be put on AUVs and you wouldn't, or unmanned aircraft, you wouldn't have to worry about the power. And we really need to get them commercially developed. So the third method on the next slide of getting your position underwater is to, right now, the National Geospatial Agency and the Air Force keep maps of gravity field and magnetic field anomalies. And when their jets are GPS jammed, they can look at the maps of gravity and magnetic anomalies, and they can tell where they're going. That's great if you're a jet going 700 miles an hour, but if you're an unmanned underwater vehicle that's going maybe 4 to 10 knots, you're not going to cross that many magnetic anomalies with the maps we have now. So what we're trying to do is use quantum magnetometers and quantum gravimeters, which are literally more than 1,000 times more sensitive than the magnetometers and gravimeters out there. So we can make high resolution anomaly maps that could potentially be used for AUV navigation. So right now, there's a couple companies that came out with some of the earlier versions that were only cooled to 1 microkelvin. The Air Force and NGA tested them, and they were unstable. but there's a couple other companies that have in the past 2 years cooled them down to 1 picokelvin, and that they've had them out operating all by themselves, and they seem to be extremely stable. Some of them have even been out on boats, but they were the size of a refrigerator and took about 100 watts of power. So now they're in the process, and by about this month, I need to call them up. I gave them the specs. They're supposed to have them smaller than a bread box and take only about 20 watts, so they could fit into an AUV or an unmanned aircraft or unmanned surface vessel to map these anomalies. As I note here, there's still a question, especially under conditions of aurora, whether or not the background magnetic field is changing and how fast the gravity anomalies change over time. This is just something that we're going to have to work on. The quantum gravimeters should also allow for monitoring of sea ice thickness and sea ice ridges. So there's a couple of other uses for those. And I'm going to run through the next couple slides real quickly here. Next slide. This just shows that these actually exist. You can go out and buy them. These are the bigger ones that I mentioned. And the next slide just shows how these work. The sensor is actually the most common one now is a diamond with a couple of empty spaces in it with rubidium atoms. And for magnetometry, you have them going in X, Y, and Z direction, and you move around and you can see they will fall in space, and you can measure the change in magnetic field and gravity. That's not the best explanation, but that's pretty much how they work. There's plenty of literature on that. I won't go into that. So the next slide just shows an example of what the current Air Force and NGA map of magnetic anomalies looks like that they use when flying aircraft. And it also shows the plane that they use to collect the data. And the next slide just shows this issue about drift. We don't really have a good idea of how fast these things are drifting around and how much they change over time. That's something that if we're going to use these magnetic and gravity anomalies for navigation in GPS areas under ice, we'll have to work on. And the thing that I didn't mention that I want to be sure to mention now is that we can map right now the spatial distribution of some of these manganese crusts. But in terms of looking at their depth, that requires point samples. But if you have a magnetic and a gravimetry anomaly map with these quantum sensors, you should be able to very accurately tell how thick those manganese crusts are. So these quantum sensors would be another way of simply driving an AUV across the area, and then you could get a map of exactly how deep those crusts are, and you could quantify the size of the resource. So a couple more slides here. Next slide is just a continuation of this. Some people seem to think that this is way out off in the future, and it's not happening. I'm here to tell you that the Royal Navy has been working on it. DARPA has an active program that's working on it. There are some entangled methods of doing this that have increased the sensitivity even further. The Brits have been flying these in aircraft to replace GPS already. The Air Force is looking into doing the same thing. And Exail, which is a big navigation company, has plans to come out with a system for maritime vessels and autonomous underwater vehicles in 2027, even though there are a couple of other ones sooner than that. So I'll just get to a couple of other technologies here. This next slide, I mentioned that we have been using unmanned aircraft. This is the most sophisticated one that I know of. This has been off of some of the Swedish icebreakers. This is called the Ortho drone. It's a very interesting drone in that its entire body stays still. So it doesn't, the wings move around, but the whole body is gimbaled. So it's always looking straight down. You don't have to correct the camera position for tilt like you do with a lot of other things. Like many of these really good drones, their cost about $100,000. But I always have to point out to people that when we're in ice ridges, my ship spends an extra $100,000 a day of fuel. So this would save you, if you could find how to avoid the ridges, you would save the cost of just a single day or a day or two's operation. So that's one of the things that I mentioned about ice ridging. And the next slide, there is a brief discussion of some of the Office of Naval Research stuff that we've been working on. They've been looking at how to get unmanned aircraft up and operating in the Arctic. They've been up in Barrow, they've tested in North Dakota. They have already been up to Thule, and they're going to be working more in Svalbard in 2025 and 2026. These are the smaller unmanned aircraft. As I mentioned, NASA is trying to take high altitude unmanned aircraft up there, medium endurance ones. And there's also an effort to do some coordination with manned aircraft with some additional sensors on there. So moving to the next slide, I wanted to get to this issue that is kind of a key thing. Okay, you have your autonomous underwater vehicle up there. How do you keep it up there for persistence? So a couple of years ago, Northrop Grumman came out with this technology, Neobicon, which uses niobium. And niobium is an element, when you put it in seawater, it forms a layer of hydrogen, so it does not biofoul. As soon as you touch the two niobium contacts together, you can pass a current to them and you can repower it. So that's one way of doing it. I also mentioned in the first bullet, there's some folks with hydromia optical modems that are also working on these kind of connections. And in the next slide, for me, the critical thing is it's easy to do this with solar panels on a mooring that's at the surface or a surface wave mooring, but I really need to be able to do this under ice. And so Dolphin Labs Technologies is here in Alameda and Berkeley. It's a Berkeley spinoff company, and they make systems that work under ice to harvest internal wave energy. And they partnered up with Scarf Technologies in Trondheim under a NATO project. And so that little E-Loom AUV just simply sits on that docking platform, and it recharges via inductive coupling. And that's transferred from the internal wave energy harvesting system that's shown there on the left. So that's inductive coupling. That's one way of doing it. It's a little bit not the most efficient. And then the next slide here, next two slides. Another way of doing this has been put together and patented by the Monterey Bay Aquarium Research Institutes with their long-range AUVs, which are called Tethys, and those are now licensed to Saab for commercial production. They partnered with Northrop Grumman, and they have a method of docking the AUV, which I'll show in the next slide here, and recharging the AUV that way. And so this is their platform, and the mooring here could be either subsurface or surface. It's irrelevant. So you can see that the mooring has its active acoustics, and the AUV has this little arm on the front of it. As it gets near the mooring to recharge, it senses the acoustics thing. It opens the arm up, and what you can't see very well, there is a socket in the arm, and that rod on the far right there is the niobium charging rod. It fits right into the socket, and there are some charging anodes and cathodes in there. And so it closes up on top of the niobium rod, and then it will charge. And then when it's charged up, the rod will open up again and it'll back out. And so what this allows is a fairly permanent mechanism of repowering yourself in the Arctic for persistent domain awareness. Right now, the Monterey Bay Aquarium Research Institute has only one system out that does this, but they are in the process of putting a cable out with a system that can recharge 3 different autonomous underwater vehicles at the same time. And each of those autonomous underwater vehicles, the way MBARI runs it, will have a different suite of sensors on it. And that's probably how we might be running it also. If you're wondering how we would be tracking hostile AUVs in the Arctic, you can track them acoustically, optically, or via their turbulence sensors. So anyway, there's a couple other slides here I'll just get through real quickly. The other method that I've talked about, the other problem that I talked about is like, okay, great. You have found a hostile AUV that's about to attack your fiber optic cable. How do you get that information back to the surface, including the position, which we already talked about, but where it is? Well, if you have your single AUV that's tracking the bad guy have to come to the surface to try and transmit the data, and it's under the ice, you have a problem. So I've been working with methods for optical communication, and we have a Navy effort that's going on for optical communication through sea ice. but there are optical methods, and just here's to show you that there are a couple of case studies that have already been done where some communication underwater has already been accomplished. And there's also at the bottom there, there's an effort that's been underway for ship-to-ship communications and ship and unmanned aircraft to surface vessel communications. So there is some effort going into this. Next slide. I'm going pretty fast here, but I wanted to make sure we got through this. So one of the things that optical communications have a problem with is marine snow, fog, and clouds. So about 2 years ago, this company, Kai Labs, came out with a method that uses orbital angular momentum to correct for turbulence and particle scattering. So this really makes things possible that weren't possible previously. And one final slide. Well, one penultimate slide. So the other thing people seem to think is, again, they think that this is way out in the future and we shouldn't be trying to do this now. There are already several Chinese quantum communication satellites in orbit. They are putting up 2 or 3 more this year and a couple more the year after that. Finally, we have some other satellites that are going up and some of the other efforts mentioned here. What I would like to see is some of our ships in the Arctic and other people in the Arctic get the communication receivers so that they could start receiving information from these quantum communication satellites. The US satellite is a couple of years behind now. It's joint with Britain, Canada, and Australia. But these satellites are going up. And this is the perfect time to start getting tests done so we could look at them in the Arctic. And then I just have a very quick conclusion slide. So my conclusion is that for persistent surveillance in the Arctic, we're really going to need long-range AUVs that can go under the ice. And they can be recharged however you want, but we're going to need those. We're going to need to know where they are. And so since there's no GPS, we're going to have to come up with some other method of doing that. We will have to try and develop some quantum sensor capabilities, magnetics and gravimetry, and that'll have a variety of different uses that can be for sea ice thickness or for measuring the thickness of mineral deposits. And then we have to figure out how are we going to do AUV to AUV communication and AUV to satellite communication. And so I've been looking into quantum communication for that. So that was the sorts of things that I was going to talk about today, and that ought to leave plenty of room for questions.
Yeah, thanks, Phil. It's always very jam-packed and very engaging presentation. We do have a couple minutes here, and there was something. Carrie, you can just come off mute if you want to ask your question.
I guess the question I had circling back to the beginning of the conversation and kind of what I had in mind before I saw the name of this was basically if you had any comment on the new or existing technologies, tools, or resources that might improve marine domain awareness from the local kind of mariner's perspective to help increase better situational awareness, or also threat/response awareness for from the perspective of local communities.
So that's, I think, where if I can get some of these aerostats or high altitude pseudo satellites, I think that's going to provide, that data will be made freely available to the local community as we have it envisaged right now. And so I think that will help people sort of they'll have a good feel for the stability of the ice edge and how much the ice is moving around. And that's the part I mentioned about the trick is as we get more of these satellites up and some of these high altitude, long endurance aircraft, that will provide the persistence, but also the high resolution, which is the sort of thing the local people would really be interested in.
Thank you.
Well, I think I'm going to take this opportunity to thank Phil for presenting to us, giving us great insight, the opportunity to comment and ask questions. So Phil, anytime you want to come back to the IARPC Tech Team, feel free to come to our meetings. We could have you present again in the future. So thanks thanks very much, everybody. Please thank Phil for his presentation.
And my email is on that first cover slide. So if anybody has questions they think of later, just shoot me an email.
Thank you, Bill.
Yeah. Thanks, everyone. And I'm putting a link in the chat to the event where you can find a copy of the slide deck.
Thanks, Meredith.
Thanks, everybody. Bye.
Bye.
Thank you.